All right, here we go. Good morning and happy Earth Science Week, everybody. We are back with an episode of Ohio Rock Talks, and we're going to talk today about the Ice Age in Ohio. Thanks for joining us. I just want to remind everyone, if you've been with us before, go ahead and use the Q&A box. And if you haven't been with us, I just want to point out that there is a Q&A box. So go ahead and put some questions in there for us if you have any throughout the program. I have with me Chuck, who is going to be helping answer questions behind the scenes. And I'm going to pass it off to our presenter today, Tyler, to go ahead and get started. There you go, Tyler.
Great, thanks, Alyssa. I'll share my screen. Okay. So, hello everybody. Thank you for joining in. I'm a mapping geologist with the Geological Survey of Ohio, and specifically I spend a lot of my time mulling over details about the Ice Age and how it relates to Ohio. So that's what I'll be discussing today, some fun details about what the glaciers did to Ohio. When I think about the Ice Age, some of the first things I think about are the environments and what the wildlife may have been like, such as mastodons and mammoths. I'll pull up my pointer here. Let's see. There. And other friends that you might have seen in like classic children's movies like The Ice Age with Manny and Diego. But as a mapping geologist, another thing I kind of focus on are kind of what are the effects of the Ice Age and what do they look like on a map. So I look at colors and lines and labels a lot because they can bring out some important features of interest that can pop out on an image or a map, and they can help tell a story, kind of like the small little reference map we have here in the middle of the screen. It shows two major glaciations to affect Ohio that we're going to get more comfortable with, the Wisconsin and Illinoisan, but these aren't the only glaciations to happen to Ohio and the Earth, as we'll talk about soon. So to kind of tell a condensed story of Earth's and Ohio's glacial past, I divvied up my talk into roughly 3 sections that overlap quite a bit. You have like the Ice Age in Ohio, get some of the basics in the background out of the way, the general geology of Ohio and glaciations and how the Ice Ages affected Ohio, and then what we are doing to map what the ice did to Ohio, why it matters, and I'll show you some freely available resources that we have that you can use for free. So to get over, what an ice age really is, essentially an ice age happens at any time in the planet's history where ice persists many, many years on Earth's surface during relatively cooler climates. And during ice ages, water that would be normally trapped or cycling around within the water cycle, evaporation, condensation, and precipitation. Now, that water kind of gets trapped at that precipitation phase. It gets stuck as trapped as ice. And then when a lot of that ice becomes trapped and stays on land, the sea levels become lower as a result. And typically all this ice forms at the North and South poles, at least in more recent geologic history, because that's where we have overall cooler seasonal temperatures that can be found. And that's where the ice tends to build up easily. So how do Earth scientists really learn about the chilly past that we have? One way is by drilling directly into the ice and glaciers and ice sheets and pulling out what we call little cores of ice, like the photo here on the left. And another is by analyzing what we can see what the ice offers within its structure, like gases can become trapped within the ice. And that gives us a good idea of what the environment and climate might have been like as the ice was compacting and forming. And a similar process can be done describing ocean or glacial sediment like we see here at the core in the middle. Or you could even radiocarbon date or kind of determine what the environment might have been like from organic things like animal shells at the top right. And we can even do something simple that you may be familiar with, is just counting tree rings. Each year shows a different ring of growth. And analyzing things like this is called using a proxy, because we can indirectly indicate what something about the past based on something we can see today. which helps, but piecing all these together helps us kind of decode Earth's history. And ice ages happen multiple times throughout Earth's history, but are overall kind of a rare thing to happen. And some are so short-lived that we don't really have much information on them. So here you'll see a nice graphical rendition of the geologic timescale. An important way to describe rocks and understanding Earth's history is by getting to know this timescale. And geologists can break down Earth's history into pretty large sections of time, like eons, like the Archean eon at the bottom, that can cover millions upon billions of years, or even eras like the Paleozoic, Mesozoic, and Cenozoic that we see vertically here that can cover millions of years, similar to periods like the Pennsylvanian and the Mississippian that we see on the right-hand side that can cover also millions of years. And you notice I put little ice cubes next to all these different spans of time that coincide roughly with when we might see a major ice age. And the largest glaciations probably happened when there was little life on Earth to really observe them. That's during a time known as the Precambrian, or the time before the Cambrian period. And the Cambrian period is pretty important because 550 or 540 million years ago is about the time when the Cambrian explosion happened, and that's when life really began on Earth and really took off in Earth's oceans. And the glaciations that took place in our young Precambrian Earth may have been so massive that this ice just engulfed the whole planet. And this is known as the snowball Earth hypothesis. And I think the scientific community might have missed out a bit on the opportunity just to call this the snow globe. But evidence of this snow globe in these ancient glaciations suggests that this may have happened about two big spans of time during the Precambrian. The first time, pretty young, and within the young Earth, 2.4 to 2.7 billion with a B years ago. And then another one that happened sometime after, roughly around 700 million years ago. We have two other ice ages that happened during this time or after that time in the Paleozoic. One during the Ordovician time, so we'll place that about 450 million years ago. We had a lot of several ice ages that happened in the Pennsylvanian and into the Permian time, about 300 million years ago. This kind of span of the Paleozoic is interesting for Ohio at least, because that's where a lot of the bedrock or all the natural rock that's kind of formed in place in Ohio is where it comes from. So all the Permian period and older, the Ordovician mostly. So that means we don't have anything above that, really. We have nothing from the Mesozoic when our favorites like the T-Rex were around during the Cretaceous period. They all died out 66 million years ago and don't have any rock evidence of that. However, as we go all the way up the time scale, we get to one instance of an ice cube, which represents the last ice age that we had in Ohio during this Pleistocene epoch, a smaller chunk of time. But rather than lithified rocks at this time, we get this loose, unconsolidated lithified or unlithified deposit we call sediment. And although this graphic is nice and pretty, the true lengths of time are kind of lost here because all these spans of time look to be almost the same, and it's kind of tough to grasp million and billion years ago and how that really relates to the Ice Age. So one way to do that is by using what we use to map, lines and colors and labels. So this long line across the screen represents the length of the Pleistocene. So that's that epoch of time where the most recent ice age happened, about 2.58 million years ago. And that tiny arrow on the right represents now, or today, which is barely a blink in geologic time. And then we can start scaling the ice age with other significant events and glaciations that happened in Earth's past. First, let's just we can compare to the dinosaur extinction 66 million years ago at the end of the Cretaceous period. So now we're saying the whole length of that screen represents 66 million years ago from today. That span of the ice age is already quite small in comparison. Let's compare this to the last time we had major glaciation besides the last ice age, during the end of the Pennsylvanian glaciations, which is about 300 million years ago. So it's already a huge jump in magnitude. And it's really interesting to think about how that huge span of time that separates the most recent ice age during one of the more significant ice ages in Earth's history. And then compare that to one of the last snowball Earth, the last snow globe, around 700 million years ago. And then we can jump all the way to when Earth was formed, 4.6 billion years ago, where in comparison, that last ice age is basically the same line as today. And you can even imagine, comparing this to the universe age, over 13 billion years ago. But the point is, Earth is pretty old, and a lot of these different events that took place, happened in a pretty short period of time, especially with, your and I's concept, the human concept of time. So now that we talked kind of about the ice ages and when they might have happened, how about the why? Why did these ice ages even happen? What causes them? It's a pretty simple question with a very complicated answer because there's so many things that can contribute to all this cooling. And some events are more or less significant in Earth's history than others. And other cycles can influence each other. But starting big, we have plate tectonics. So we know now the continents are constantly moving slowly away from each other or towards each other, possibly standing still for a moment. But these movements not only alter how much land is exposed at the sea, but also create and seal off different oceans, and that kind of alters the ocean currents and distributes heat differently throughout the globe. Most of the warm water that's just towards the equator can be moved towards the cooler latitudes, like as we get closer and closer to the poles, for example. And all these continents were shaped differently and positioned differently throughout time, and that causes a really interesting dynamic change of climate as well. So what you're looking at now is called a paleogeographic map, and it shows what the Earth might have looked like about 450 million years ago. So it shows where Ohio is with respect to kind of some of the other ancient continents' positions, and this is during the Ordovician, about where that glaciation period once was too. So we see that all the white here represents the glaciation at the South Pole. But another thing to notice is that Ohio was actually pretty close to the equator. It was actually south of the equator. That's what this red diagonal line is here. So though Earth was in an ice age, the local environment to Ohio was probably quite different. It was probably warm and tropical with a shallow inland sea, since we're near the equator. So this region of Ohio was affected a lot during any changes of sea level change caused by the ice age happening at the South Pole. And another factor throughout time is the abundance of greenhouse gases in the atmosphere. That's a pretty hot topic today, and I won't really get into much of the details, but essentially when Earth has high levels of gases like carbon dioxide, water vapor, and methane, and all this combined with other factors, we get shot into what's called a greenhouse or a hothouse condition. That makes the Earth overall pretty warm with an overall pretty humid environment, with little to no ice accumulating year after year after year. And when we get more oxygen on the flip side, or maybe less concentrations of CO2 in the atmosphere, perhaps that CO2 is trapped someplace else, we tend to get more icehouse conditions. So that's when we might have more instances of ice sheets to grow. And organisms affect this trend a good bit in some cases in geologic history. The most one being our little friends, the cyanobacteria. And that's the most notable because it affected the atmosphere by photosynthesizing a lot. And that was during the end of that last snow globe or snowball Earth around 600 or 500 million years ago. And there's a lot of other natural causes. One I'll mention perhaps is volcanism, which it can expel a lot of sulfur and other gases to alter that atmosphere. It can also cool the Earth briefly by giving like an umbrella, like an ash cloud that kind of reflects some of the sunlight a little bit or internally cool the Earth. But it can be pretty tough to pinpoint, one direct cause for the ice age. And there are many other factors as well, but mostly what I just talked about are factors that influence the ice ages within the Earth itself. But the major factor is more extraterrestrial away from Earth, which is the sun. The interaction of the Earth and the sun specifically. Because most studies suggest that a lot of this recent, the cooling trends over the past several 100,000 years might be best explained by the Earth's orbit around the sun. Because during some of these cooler cycles, you'd have more snow that can fall during the winters than could be melted in the summers. And this happened for several different reasons. One of the most important cycles is how much sunlight and radiation hits Earth and cycles that affect that. And this all depended on the Earth's tilt, its wobble on its axis, like its precession, and its orbiting distance around the sun, which is what we call the eccentricity. And this is all known as the Milankovitch cycles based on the mathematician that proposed that idea. But let's talk about why this all really matters. So looking at the figure on the right, we know this equator is known for being really hot today, mostly because that is where it gets the most direct sunlight on the Earth's kind of bulge facing the sun. And you get less and less solar heat and radiation that make it to hit the Earth the further and further away you get from that center equator line. And these happen to be the cold places where ice tends to build up during icehouse conditions. And the Earth's orbit around the sun affects climate probably the most naturally because this eccentricity value, it varies from being about near symmetric and round to being a little bit slightly more of an elliptical orbit. So it's not quite as extreme as this kind of figure shows. But this eccentric orbit influences the amount of solar radiation that can hit Earth or give Earth the opportunity to absorb directly. And this cycle changes about every 100,000 years or so. And as we see, we tend to get major swings in climate about every 100,000 years as well. So we have that cycle overprinted upon other cycles like how the tilt changes about every 41,000 years. Right now it's about 23.5 degrees. That ranges from as little as 21 to about 24.5 degree variance. And the bigger that number is, the steeper that angle is, the more time the poles spend facing the sun. So this causes, more extreme seasons. So you get warmer warms and colder colds, and these cycles are a little bit more intense. On the opposite side, we have lower tilts, which causes less temperature variation. So you get slightly cool summers, you get some hotter winters, which is actually better for ice because it gives ice a chance to survive the really hot summers or compared to the really cold winters and the really hot summers. And as you may know already, all these, the existence of this tilt causes the seasons within the Earth. And so basically the amount of this tilt influences how intense the seasons are. Then you have the wobble, like wobbling on the top, the Earth wobbles on its axis as well. And that's kind of superimposed on all these other cycles as well. So now we got the general sense of, what these glaciations, how they're made throughout time, and then some factors that kind of help explain how ice made it into Ohio. Now let's kind of visit the ice ages that did directly affect Ohio's present landscape the most. So I'll start this map depicting what is the last glacial maximum, so the glacial limit of all the ice invading all the way from the North Pole all the way into the northern tips of the United States, North America. And ice and snow began piling up as a sheet of ice around Canada and the North Pole, and would shrink and expand in different cycles. And it expanded all the way to Ohio, and then you'd have instances where the ice is retreating all the way up all the way up to the north, which is what we see on the right here too, which is the interglacial period, or times when it's a little bit warmer and the ice is overall kind of getting smaller and shrinking and retreating. And this ice sheet that was the last glacial maximum limit here probably ranged to be about 100 or hundreds to even thousands of feet thick in Ohio. So it's interesting to think about, what did all these advances and retreats of thick ice actually do to Ohio? So for that, we're going to look at a very simple glacial map, and we're going to fill in some major zones here as we talk about them. So first we have the unglaciated part of Ohio to get that out of the way in the southeast Ohio, where the ice didn't quite make it. And these other zones here are areas where we have instances of glacial deposits and direct evidence of ice. But here, it's a pretty mountainous terrain, mostly due to the Appalachian Mountains, which made it kind of tough for ice sheets to continually kind of weave their way through all that the rough terrain. And then, currently we understand about 3 major ice ages and glaciations within the ice age that affected Ohio. during the Pleistocene. These are named after Midwestern states where we have a lot of evidence of these glacial deposits, and they're named after places where they were first studied. Excuse me. So in Ohio, in the first major span of time that we have evidence for that contains the oldest glaciations, is this little section down here, the pre-Illinoian. That's pretty poorly understood because we don't really, it's such a long time ago, and we don't really have very much direct evidence of it. But right here around southwestern Cincinnati, we know that perhaps these glaciations stretch even further down to Kentucky or maybe parts of other states as well. But they've been on the landscape for a very long time. So things like water and wind eroded them down, and being exposed for so long left them, pretty weathered out. And then later, we have the Illinoian glaciation to happen, and that's when ice stretched all the way from the north to the south and reached to about this dashed line boundary that we see here. And this destroyed and overtopped all the previous older glaciations from the pre-Illinoian. But these are also pretty old. The Illinoian deposits are old and weathered out too, similar to the pre-Illinoian deposits. But then we have the most recent and last glaciation to affect Ohio, and that's called the Wisconsin. And that destroyed and overtopped everything else, all these other older glaciations, and extended to the black thick line. So not quite as far as Illinois in most places, except for right about here. And these glaciations carried and left behind glacial debris that covered the lands of Ohio, and the major deposit is being till, which is where we get the till plain name from. That's this relatively soft mixture of sands, clays, boulders, and other glacial debris that the ice plowed, transported, and left behind when the ice melted away. And glaciers picked up rocks and soils and wildlife, and sometimes much older rocks too within these tills and other glacial deposits. And that's why a lot of the regions on the left here are separated by different planes of till, which are till about around the same age. Although some of these areas get a little bit more complicated than that. There's a section to the north I didn't really talk about yet, and that is the lake plain. That's an area where mostly younger the deposits than all of these were, and it's where a lot of stages of a much bigger ancient Lake Erie once filled the land, kind of like an overfilled bathtub, because Lake Erie's right up here. So the combination of all these previously mentioned glaciations, each with the tremendous force, you have all the massive weight of the ice, you have all the rocks within the ice, and the power of the melting water that helps shape the land underneath the ice, that help form a little basin up here where that was once where Lake Erie was, or is, but other forms and stages have been. And that also helped form the glacial grooves that you can see right here on Kelly's Island today as well. But on Lake Erie shores, most of the once lake and beach dominated landscapes were deposited towards the end of the Wisconsin period as the ice was kind of advancing and retreating away to the north out of Ohio. As you can see from this map, glaciers can impact the landscape with a lot of ice and water, but the glaciations probably extended a little bit further than these glacial lines that I showed here. So we have evidence of glaciation, or the effects of glaciation outside in the unglaciated area as well. So as I mentioned before, the pre-Illinoian represents a pretty big gap of time where we don't know much about the landscape. So to look about what happened to the land before and during and after glaciation, I have a few pictures here. The pre-Illinoian glaciations were the first to really drastically erode and invade the landscape, and it destroyed major drainage pathways and stream systems. And that major drainage that kind of ran across Ohio's surface is the now buried, or mostly buried, Taze River system. And it's like a Grand Canyon-like river system that's buried underneath Ohio, and it's somewhat disconnected in places, and it's pretty difficult to map because it's completely buried by hundreds of feet of glacial drift. So not exactly a river anymore. And it's kind of tough to visualize without a map of the subsurface. But we do know that it originated from the south near North Carolina, and then it once flowed all the way north and then northwest through Ohio, and then eventually drained all its way into what is now the Mississippi River embayment. However, you can see evidence of the Tays pretty easily outside of the glacial boundary on aerial photographs. So look at this, large and broad meandering valley here in Ohio, in southern Ohio, on this Google Maps photo on the right. This red line shows about where the boundary is, the glacial boundary of the Wisconsin-Illinois glaciations. This valley in Ohio here doesn't have one solid river that runs through it anymore. This is actually plugged at one point with sediment when the glaciers dammed that northwestern flow of water within the Tays. And since that land is smoothed over and it's pretty farmed, and the surrounding landscape is pretty rugged and forested, it pops out kind of easily on a map. This blue line shows about where that Tays continues if you were to keep drawing it beyond the bounds of the glacial boundaries. So to imagine kind of like what all these processes might look like, and to get an idea of what what this landscape would look like if you were to take away all this glacial sediment, you might want to look at something called a bedrock topography map, which we will get to see later. But to see what a landscape looks like during glaciation, here's a little block image showing what the landscape may have looked like, with some common glacial features being formed like moraines. And many people have this misconception that glaciers just simply bulldoze over the landscape, but the process is pretty more dynamic as the ice kind of molds around uplands and can funnel into lowlands. And glaciers and meltwater can erode and carve out sections of the landscape, but they also deposit a lot, so the glaciers can destroy and they can create. This is evident on the landscape after glaciation. Now, the landscape is completely different, with interesting glacial landform shapes, all formed by some combination of ice and water. And some parts of Ohio look like this, mostly within the till plains of Ohio, which is mostly dominated by the ground and end moraines. This is a quick reminder about what these moraines are made up of. It's till, that glacial material that has all the large mixtures that the glaciers picked up and deposited within its travels. And these materials can travel hundreds and hundreds of miles, and we know that because of the things that are trapped within the tills and other materials. In the presence of interesting rocks don't quite belong to the native landscape of Ohio, like volcanic rocks even. And these weird rocks are called glacial erratics, and they can originate as far up north as into Canada. But till isn't the only thing that can be brought upon due to glaciation. We have other deposits, such as sand and gravel, which can be deposited in various ways. Sometimes known as outwash, these large pieces of rock can be forcibly washed out or pumped out of glacial meltwater and can get funneled into valleys. This high velocity water can carry large particles like sand and other erratics and things on the left. But we have the opposite end of this fast high energy environment, a very calm environment like a glacial lake. When this can happen, when glacial meltwater gets trapped between ridges or in front of a glacier. So we get these lakes that form, kind of like ancient Lake Erie, or maybe a small plug tributary of the Tays or something. And these situations allow for small particles of clay and silt to slowly deposit over time into thin layers that you can kind of see on this image here on the right. So you can think of these opposites kind of being like the tortoise and the hare, go very slow and then very fast, different environments. And then you have the till that's kind of mixed in between them. So now we went over the three big major glacial materials in Ohio. We have the mixed till, the coarse sands and gravels, and the fine-grained clays. And each of these three materials might help indicate the environment that deposited them, but we can also find even more evidence of what the land was like within them. So as I mentioned, glacial ice can pick up and bury other parts of the landscape with it, and that tells us more about the environment, what it was like when the glaciers grew over them. And on the left here is a photo of some wood, ancient wood stuck in glacial till, and this wood, rather, it's probably about a 20,000-year-old conifer tree, which generally can indicate a pretty cold climate. So looking at and getting an age date on vegetation like this is another piece of the puzzle that fits into the story of the Ice Age. But when it brings up a point, because when you think about ice ages in the landscape, images of white come to mind. You think of snowy and frozen tundras. And although that was true at certain points in time, interglacial periods and times where we didn't have glaciers invading a landscape, in Ohio might have looked a little bit more like these images. Could be a damp, swampy forest area, or maybe expansive grassland that were pretty cold and dry. And different types of animals like to live in these different types of ecosystems. And some were not some of these animals aren't drastically different than today. Because the animals that are around today were still around during the Ice Age time. Some of them, within over 10,000 years ago, like salamanders or raccoons. Although some of them are not really as common in Ohio anymore, like bison and muskox. But we have some more famous extinct organisms that were around from that time. We can usually call them megafauna, such as the giant beaver and the stag moose. And these animals likely thrived in these very delicate habitats, or maybe had adaptations that made them endangered during times from these extreme climate shifts away from near glacial conditions. Or perhaps the onset of humans came and overhunted them, but that's a different story. But each of the effects of glaciations on these organisms were felt by other organisms up the food chain. So another set of example of extinct organisms and mammals that you may be familiar with are the fierce Pleistocene predators, such as the mighty short-faced bear or the direwolf. So these were also affected by changes of the landscape in Ohio and the climate. So we can use almost any organism ranging from large megafauna like this to even small snails to really get us and help us figure out what happened at a spot during the Ice Age. For one example, I'd like to touch on a famous set of Ice Age megafauna that were once in Ohio, the mammoth and the mastodon. And people sometimes get these two confused since they both kind of look like elephants. They both were herbivores and they have long trunks, but mammoths are actually a little bit more evolutionarily close to elephants that you might find in Africa or especially Asia, whereas the mastodons are a little bit more distant. But mammoths were larger, they were slimmer, they had a little bit more of a humped back, which might be related to how they kept warm. And we think they like to live in more open grasslands where they could eat small grassy plants. And we think that because their lifestyle can be indicated by the type of teeth that they have. So this tooth here shows this really flat ribbed part, and the spiky part at the bottom would be the roots that go into the jaw. This is made made for grinding plants in small woodier or less woody material. Mastodons, on the other hand, are a little bit smaller, a little bit more muscular, had flatter heads, and they probably like to live in more forested type areas where we had more trees and woodier plants that could grow, because their teeth were a little bit more cusp-dated and pointed, and they're designed for breaking apart, thicker, woodier types of plants. And these stringers down here are the roots that connect, and that would be in their jaw. So we can kind of determine how much of their populations are in one place, and then link that to the type of habitat that we think they might have been found in. So you can combine all these different pieces of the puzzle, ranging from what the glacial deposits look like to evidence of specific animals or vegetation. It makes it a pretty interesting job for a geologist to figure out why the land looks the way that it does today. I touched on a little bit about everything that's kind of Ice Age related. So now we're going to get into why it matters to Ohio and start talking about different types of glacial geology maps that we have and what we can use them for. So to the right, is this interactive geology map that the Ohio Geological Survey created to allow the public to easily explore these different types of maps that we have. And so it's going to be fun to play around with all these different map layers and see how different areas are different than another. You can do that yourself by going to the website link that I have up here, or just typing in OhioDNR Geological Survey interactive map or something on a search engine. So this one I'm showing you right now is what's known as the Quaternary map, and that's a period of time, of geologic time, that represents the Pleistocene to today. So the Ice Age up to modern day times. And these types of maps are used for general education type guidance and can guide geologic interpretations for the area's glacial history. And they give an idea of the types of landforms that we see from glaciers and what type of processes might have happened to contribute to make up the ground. To get a little bit more detail, you might want to look at something that we have called a superficial stack map. And these are used kind of similar to quaternary maps, but they provide a little less information on the glacial history and focus more on what that material might be, like sand or clay, and how thick it might be if you were to dig past each layer of, sand or clay. And these maps are a little bit more complex, and you can use them to answer questions like, what's underneath my property? Or, water well drillers might use them to wonder how deep they can drill until they can get to hit, sand and gravel, aquifers and groundwater and things like that. Land planners could use them for construction. Mining companies could use them as a reference for new mining operations. There's so many applications for this. And we recently finished this mapping of the whole state, this superficial stack map, recently in 2021. And it's an over 20-year effort, so it takes a lot of time to map this type of geology. Then we also have bedrock topography maps, and these show what the landscape would look like if you removed all that glacial material and it uses different colors to represent different changes in elevation, high and low elevation. So it's kind of like looking at Ohio with X-ray vision. This is used to figure out different aspects of glacial and pre-glacial drainage history, where buried valleys such as the Tays may be located. And it's also very fundamental to other maps too, like bedrock geology maps, since the elevation of what the bedrock would be buried underneath all that, buried beneath the subsurface might change what bedrock unit might pop up underneath the ground if you were to strip away all that glacial material. And then we have kind of a twin map to the bedrock topography. They're very similar, the drift thickness map. But this shows a simple understanding of just thickness, how thick that unconsolidated glacial stuff is, or the drift as we call it, is on top of the bedrock topography. And each color represents a range of thicknesses in feet and outlines thin drift areas in yellow, oranges, and greens, and thicker areas in blue and purples and pinks. And the thickness is similar to the stack unit thicknesses that we have in the superficial stack map, but this map doesn't provide any information on like if it's sand or clay, what that material is composed up of. However, it's a little bit more precise in terms of thickness, so it might be interesting if you want to know if it's 153 feet to hit bedrock or something, if you're drilling a well or something. So these types of glacial maps have all these different applications ranging from groundwater resources to construction to getting an idea of what the Ice Age history was like in an area. But you really get the full effect of them if you use them all together. So let's kind of see what an area looks like that has Ice Age evidence around by looking maybe at the 3 Cs, the Cincinnati and Cleveland and Columbus area, and then other parts of Ohio, just to see what these areas look like using our maps. So we'll start with Cincinnati. We'll delve into the quaternary map. There's Ohio statewide quaternary map that was made in 1999 and is mapped at a scale of 1 to 500,000. That basically means that if you zoom in too much, you will lose some detail and it isn't the greatest. But you can see trends. And the legend on the left is quite long. It's longer than what fits on the screen. But you can see there's a lot going on here. You have this yellow area is alluvium, so that's related to rivers and valleys. And you have lake deposits, and so we got silts and clays along the valley edges of different ages. We also have the rare occurrence of the pre-Illinoisan, that's this KG and KD on the left here, that are very weathered and dissected out by water over the past several 100,000 years. And you even have some outwash here on the Ohio River Valley. But let's say we were interested in the small area of Norwood, and this label is here. So here you can see that the Norwood is IG, which we look at our legend, it's a ground moraine, and I means Illinois, and so Illinois ground moraine. So now we know that the Illinois glaciations and the pre-Illinois glaciations all stretched all the way to Cincinnati, but we don't have too much evidence for directly from Wisconsin age glaciers. But to learn more about what's underneath Norwood, we'll have to look at some of our other maps. So to look at the materials and the thicknesses beneath Norwood, we'll switch to the superficial stack map. And there's a lot more lines and colors here, and the map shows a lot more detail than the last map we looked at. But if we focus on Norwood again, we're going to digest this complicated map label of TI6 over CI2 over TI6 LC13 over LSSH. And we have a pretty detailed legend that fits here, and then we have one on our website as well. But the letters at the beginning pretty much indicate the type of the material. So TI, till, of Illinois in age. And the number next to it just represents how thick it is if you multiply that times 10. So 6 is 60 feet thick. And then the C's and the LC's give you different ideas of types of clay, pretty much. And at the bottom, LSSH doesn't have a number with it. That's when we hit the bottom. That's the bedrock. Limestone and shale. So if you wanted more information past that, you'd have to go look at a bedrock geology map or something else. But if we want to know a little bit more precisely about how thick all these materials are, what the bedrock surface looks like, we'll have to look at our bedrock topography or drift thickness maps. So the bedrock topography shows that there we have a lot of deep green, showing deep and lower elevations, and we have transition to lighter greens and reds that represent higher elevations. And the bedrock topography of this same area tells us that more about this hidden, really thick, buried valley system that's around the Norwood label. And if you recall, this part of Ohio is about where that tributary to that ancient Taze River system resides. So part of that tributary meets up here and flows into the Taze. There's actually a piece leading into a valley called the Old Kentucky River. But for now, let's kind of see how this buried valley influences how thick all that glacial material is for this area. And we can also see how accurate the stack map might have been too. So we can see all these different colors that represent different ranges of thicknesses. Around the Cincinnati area, we have yellow that's thin to rock, and then the deeper greens and blues that show deeper and deeper thicknesses, footages. And this shows that that partially buried valley system around Norwood is about 226 to about 300 feet thick. But remember, this map is interactive, so you can click anywhere you want to get an idea of how thick it really might be at that point. So if we click about here, we get an idea of that the depth is about 256 feet, which agrees pretty well with what the other superficial stack map told us. So this is great that it agrees. That doesn't always happen because these maps were made at different times by different people with different amounts of information. But that's what keeps the Geological Survey busy. There's a lot of work to be done to make these maps even more accurate and as detailed as possible. So I have a rough idea of what the ice age is like in Cincinnati now, but you might live in or be interested in a different area around the state. So let's quickly jump to the other side of the state. We're going to go to Cleveland all the way to the north. And as a quick frame of reference, here you can see most of Cuyahoga County, and the northern blank area is Lake Erie. So we can blanket the quaternary map for this area, and we get a better idea of the extent of what these light blue and gray colors might mean. That's the extent of the ancient Lake Erie, where it once was. I have these stringers of darker blues and worm shapes that show different beach ridges, so areas where the lake levels may have been on the land surface. And then you have some modern yellow, more alluvium stuff that follow the rivers and valleys, like the Cuyahoga River Valley. And the southern and eastern part of this shows these colors that represent different types of moraines, which are from mostly Wisconsin age ground moraines. Let's zoom to the middle of the state, near Columbus. We see most of Franklin County. And I've decided to use an example of the superficial, the stack map for this area. And I kind of removed all the clutter of all the extra lines and labels. And most of the area is covered by till, as you might expect, that Wisconsin age till of different thicknesses. But these maps can also show areas of significant mining as well along the valleys, things that humans have done. So this cross-gridded pattern down here to the south shows where a lot of sand and gravel is being mined around the Scioto River, because that's kind of connected to outwash terraces of a lot of sand and gravel that in some areas are a lot over 100 feet thick. And then we have, conversely, on the other side of this snapshot of the map, we have this gray area to the northwest, which is mostly just bedrock near the surface. We have like almost nothing in this area that's from glacial materials. So it shows how variable an area might be. Although this area is all covered with glaciers and ice, the ice kind of deposited in different thicknesses and layering locations, and humans utilize it in different ways. And finally, just to zoom out at this multi-county scale about bedrock topography and drift thickness and see how what we can figure out from these maps. So to the left here is Indiana. We're zoomed out a good bit. And this, you can follow this dark wiggly line that mostly represents the buried Taze River system, which has a lot of little interesting twists and turns and little weird tributaries that splay across the state, kind of like veins. And it'd be nearly impossible to see what this looks like without this type of map. So like I said, it's kind of like having X-ray vision to see on Ohio's surface, to see past all the soft glacial stuff. And these complex drainages are also seen with the drift thickness map. You can show thick valley packages along with all the till-filled moraines and a whole bunch of other stuff that make up and fill these valleys. And some of these valleys are filled with sand and gravel packages that are great for extracting water out for us to use for groundwater sources. So you could spend a lot more time exploring all these different landscapes and effects of the Ice Age, but I'm going to leave it now to you so you can investigate the Ice Age yourself and learn more. So I hope now through this presentation, you have a better idea about why 2/3 of the state looks the way it does and how it affects the lives of people living there and what we can learn to utilize our different natural resources. If you want to learn more, you can download different publications from our website. You can read web pages for basic information. You can play with our updated online interactive map. Or you can even use this website to contact me or another geologist if you have a question about Ohio's Ice Age or anything geology related. So you can go to our publications page and just search for something that you're interested in, or maybe even a location, like whatever specific county you're in, just to see what we have available. Some of my contact information for now, and thanks for listening to me talk about one of the most interesting geologic events that happened to Ohio, and we can open it up for some questions now if anybody has any.
Thank you, Tyler. And yeah, if anyone has questions, please go ahead and put them in the Q&A box. Tyler, you did a great job covering everything, so I'm not sure if you left many areas for questions to be asked because you did such a great job. But I also want to make sure to point people to the link that Chuck shared in the Q&A, where you can get more info about the events going on this week celebrating Earth Science Week. We have stuff planned throughout the week. You can click on a day, see what events are going on. And at the end of the week, if you want to join our special event to explore further, there's going to be a fossil hunt, a guided fossil hunt on Sunday, October 17th. Which is always fun with our paleontologist, Mark Peter, at Cedar Creek State Park. But Tyler, I don't see any questions coming in. So
Okay.
Chuck or Tyler, do you have anything that you want to say before we wrap up?
Just remind folks to check out some of the other events. We've got a really great lineup this year, and the weather is looking pretty good for most of the week, so it's a great time to join us.
Yeah, absolutely. And as always, our webinars are recorded and they will be available on our YouTube page. So if you missed something today and you want to check it out again, you can find this on the OhioDNR YouTube page. As well as all of our other Ohio Rock Talk episodes. So thanks everyone for joining us and happy Earth Science Week. Bye.